So in chapter 17, we're going to be talking about reactions of aromatic compounds, and we spent chapter 16 talking about aromatic compounds in general, and here we're going to be looking at reactions of them, primarily with just benzene. So these reactions are called electrophilic aromatic substitution reactions, or EAR reactions, and they all involve substituting an electrophile for a hydrogen on an aromatic ring. So essentially we're taking benzene and doing a transformation, essentially just replace one of the hydrogens with an electrophilic compound. Right? In this case, this example here is bromine. Okay, and all these reactions will have the same general format, which I'll highlight as we go through them, but they all have some sort of electrophilic source. Right? In this case, we have a source of electrophilic bromine, which we're indicating by our positive charge here. Right, this source of electrophilic bromine and some sort of catalyst. Right, in this case, we have this Lewis acid catalyst here with this metal, which we don't see very often, but we'll see more of these metal reactions going forward. And so what is the mechanism here? Right? What's taking place? So we talked about how these benzene rings aren't really reactive, right? These aromatic compounds are not reactive. They're not reactive in the traditional way, right? Because normally, right, and we've seen this before, when we have for example, if we just had an alkene with Br2 and an inert solvent, we would have a reaction where we end up adding on the bromine, right, anti. But here that's not the case, right? This doesn't react in the same way. Because mostly Br2 is not electrophilic enough for benzene, right? We need a really electrophilic source. So what happens here with Br2, right, we discussed back in chapter 8 that one of the bromines is a little bit electropositive and the other is a little bit electronegative, and we sort of induce that really heavily by having it coordinate with this Lewis acid here. So we get this really induced effect of a really electronegative bromine and a really electropositive bromine, right? The end of the Br2 here is coordinating with the iron. And so what we end up having occur is the benzene ring can now, right, it's now ready to attack that positively charged bromine like this. And so what we get after that is this intermediate here where we have bromine, a hydrogen, and the other carbon is positively charged. So this is our intermediate here, along with this iron Br4 complex. So this intermediate here is called a, this is our reactive carbon intermediate, or you might see it in your book called a rhenium ion intermediate, or a Wayland intermediate. It all just means the same thing, that it is this sort of in-between step between our benzene ring and our substituted benzene ring. So in the last part of this reaction, what ends up happening is, right, we really want to reform that benzene ring. So we actually end up getting, and I'm going to erase the complex here to make it look more like it actually would. Right, we still have this sort of Br minus complex here, so we end up having this bromine, right, come in and attack the hydrogen to reform our aromatic compound, which it really wants to do. It was now this bromine attached to our benzene ring here, and we regenerate our catalyst, which is, the point of a catalyst, right? We want to regenerate it at the end. And so the big takeaways here, right, what seems to be happening, and the driving force for this reaction is, right, we need a very electrophilic source, right? In this case it's bromine, but we can react to other things too. And we are reforming aromaticity. Because once we get to that intermediate, we really want to drive the reaction forward to get to the final aromatic product. Okay? And we can also do the same general reaction here with Cl2 as well as iodine as well, right, with some sort of Lewis acid catalyst. Same mechanism, same everything. And in general, all these mechanisms are going to be the same for further reactions too. So we'll take a look at a couple more here. Right, so obviously this is going to be kind of a reaction-heavy chapter, kind of like we've seen with a few previous chapters here. So this next example here, we're adding on a nitro group. So the final product of this reaction looks like this. It doesn't matter where you're putting on your groups here. You can also call it this, NO2. This is a Zwitter ion, meaning even though it's charged, it's overall neutral. Right? So this is a nitro group. And what's happening here is, same as before, we have this sort of electrophilic source of NO2, and we have an acid catalyst. Okay, and the general mechanism, and we'll go through this kind of quickly, and some of these mechanisms, even though I'm writing them, we might do them in class together again and things like that, but you don't need to inherently know these mechanisms. But what we do really need to make sure we're being aware of here is that we know what the rhenium ion intermediate here is and what it's doing. Okay, so for this reaction, right, we have this electrophilic source of bromine. This nitric acid will react with sulfuric acid here to generate this intermediate. Right, we have a lot of charges on this compound, which is not something we typically see, right? It's inherently very unstable. So it'll undergo this pathway here of making a double bond to the nitrogen and kicking off water as a leaving group, which we know is a really good leaving group. All to get to, and this is kind of the big key bit here, to get to this electrophilic, right, clearly electrophilic intermediate, which our benzene ring, rare aromatic compound, will react with to get to our intermediate, right, NO2, hydrogen, positively charged, right, very important, that positive charge always needs to be there, and some sort of base will come through and deprotonate it, right, which could be, for instance, water or our acid catalyst, right, the SO4H minus, something will come through, some sort of base will come through to deprotonate that hydrogen, right, and reform aromaticity, which is the key part of this, of these reactions. Okay. And this last reaction we're to look at here, we won't cover this mechanism, right? Maybe we'll do it in class if we have time, but it's the same trend where we have an electrophilic source of, in this case, SO3H will be our electrophilic source. This is our acid catalyst. And our product here for this reaction of SO3 will be this. Where we have the sulfur group here, which we could paraphrase or condense as this. And I'll leave this mechanism up to you to do, but these are the three kind of very simple electrophilic aromatic substitution reactions that we need to know, okay? The mechanism for them, well, important, it all kind of boils down to the same thing, right? We're forming this rhenium ion intermediate. With a positively charged carbon on there that it wants to get rid of, right? So this is the intermediate for all of these reactions. And we'll see in further chapters, right, more examples of this, right, more examples of these electrophilic aromatic substitutions, but also more examples of what happens when we add substituents to it, right, because that's going to inherently change the actual reaction itself, okay, and what happens during the process of the mechanism reaction.